the integral formulas for hyperbolic functions. Since the derivative of hyperbolic cosine is equal to hyperbolic sine, if I take the integral of hyperbolic sine, I get hyperbolic cosine. Don't forget to add the constant of integration as well. Since the derivative of hyperbolic sine is equal to hyperbolic cosine, so if you take the integral of both sides, the integral of hyperbolic cosine is hyperbolic sine plus constant of integration. Since the derivative of hyperbolic tangent is hyperbolic secant to the second, if you take the integral of both sides, the integral of hyperbolic secant squared is hyperbolic tangent plus constant of integration. The derivative of hyperbolic cotangent is negative hyperbolic cosecant squared. So when you take the integral of both sides, the integral of hyperbolic cosecant squared of x dx is negative hyperbolic cotangent of x plus c. The derivative of hyperbolic secant is negative hyperbolic secant times hyperbolic tangent. So if you take the integral of both sides, the integral of hyperbolic secant times hyperbolic tangent is negative hyperbolic secant plus constant of integration. And finally, if you take the derivative of hyperbolic cosecant, it is negative hyperbolic cosecant times hyperbolic cotangent. So when you take the integral of both sides, the integral of hyperbolic cosecant times hyperbolic cotangent becomes negative hyperbolic cosecant plus constant of integration. So we learned that hyperbolic sine is defined as e to the x minus e to power minus x divided by 2. What are we going to do? We're going to take the derivative on one side and take the integral on the other side and show how we get to the next part. So if I ask you to find the derivative of hyperbolic sine, we're going to say that, hey, this is just the derivative of e to the x minus e to power minus x divided by 2. Or as you remember, you can write this guy as a half the derivative of e to the x minus e to power minus x, or in simpler form, you have a half times the derivative of e to the x minus the derivative of e to power minus x. In terms, it can be written as a half. The derivative of e to the x is e to the x. The derivative of e to power minus x, you get a negative sign in front of it. So you have minus e to power minus x and close up the parenthesis. So you have a half e to the x plus e to power minus x. And by definition, if you write this guy as e to the x plus e to power minus x divided by 2, it is basically the hyperbolic cosine of x. So the derivative of hyperbolic sine is hyperbolic cosine. Now, what if I want to take the integral of hyperbolic sine, right? In taking the integral of a hyperbolic sine of x dx, you are taking the integral of e to the x minus e to power minus x divided by 2 dx. So as you remember, you can write down this a half in front of the integral and take the integral of e to the x minus e to power minus x dx, which in turn is equal to a half integral of e to the x dx minus the integral of e to power minus x dx. This can be written as a half. The integral of e to the x is e to the x and then minus the integral of e to the power minus x using u sub gives you negative e to the power minus x. And then close up the parenthesis, and you get a half e to the x plus e to the power minus x. Let's have the constant of integration as well. And this guy is nothing but e to the x plus e to the power minus x divided by 2 plus constant of integration, or hyperbolic cosine of x plus c. So the derivative of hyperbolic sine is hyperbolic cosine, and the integral of hyperbolic sine is hyperbolic cosine plus constant of integration. And this is the algebra behind this. So let us do the same thing for hyperbolic cosine. If you have hyperbolic cosine, what was the definition of hyperbolic cosine? Hyperbolic cosine is defined as e to the x plus e to the power minus x divided by 2. So let us find the derivative of this guy first. d dx of hyperbolic cosine of x is the derivative of e to the x plus e to the power minus x divided by 2. In terms, you can write a half in front of the derivative. You get e to the x plus e to the power minus x. So you can separate this now. You have a half times d dx of e to the x plus the rate of change of e to the power minus x with respect to x. This can be written as a half. The rate of change of e to the x, as you remember, is e to the x plus, now for e to the power minus x, you end up with a negative sign, negative e to the power minus x, and then close up the parenthesis. Well, this is a half e to the x minus e to the power minus x, or e to the x minus e to the power minus x divided by 2, which by definition is nothing but hyperbolic sine. So the derivative of hyperbolic cosine is hyperbolic sine. Now, what if we want to know what is the integral? If I ask you to calculate the integral of hyperbolic cosine of x dx, it is the integral of e to the x plus e to the power minus x divided by 2 dx. So as usual, write down a half in front of the integral of e to the x plus e to the power minus x dx, which can be written as a half integral of e to the x dx plus integral of e to the power minus x dx. This is equal to a half. The integral of e to the x is just e to the x. The integral of e to the power minus x using u sub is minus e to the power minus x. Then you can just distribute the negative sign, and this guy is written as a half e to the x minus e to the power minus x plus constant of integration, or you get e to the x minus e to the power minus x divided by 2 plus c. But what is the definition of e to the x minus e to the power minus x divided by 2? It is equal to hyperbolic sine of x plus constant of integration. What's the definition of hyperbolic tangent? Hyperbolic tangent of x is defined as hyperbolic sine of x divided by hyperbolic cosine of x. So remember the definition. For hyperbolic sine, you have e to the power x minus e to the power minus x divided by 2. And for hyperbolic cosine, you have e to the power x plus e to power minus x divided by 2. And as we saw, we can cancel out the common denominator, and this guy becomes e to the x minus e to power minus x divided by e to the x plus e to power minus x. So let us find the derivative of hyperbolic tangent. If I ask you to find the derivative of hyperbolic tangent of x, you're basically finding the derivative of the quotient here, e to the x minus e to power minus x divided by e to the x plus e to power minus x. From calculus, remember that if you have f divided by g and you want to take the derivative, it is f prime g minus f g prime divided by g squared, which is your quotient rule. So this derivative can be written as the derivative of the numerator e to the x minus e to power minus x derivative times the denominator, which is e to the x plus e to power minus x minus the derivative of the denominator, which is e to the x plus e to power minus x derivative times the numerator, which is e to the x minus e to power negative x. The order is not important. When you simplify the whole thing, it becomes the exact same result. So let me move this a little bit down here. Okay. Divided by, now take the denominator and raise it to the second power, e to the x plus e to power minus x to the second. You don't have to write this in extended form right now. Just take the derivative and simplify as much as you can. So this can be written as the derivative of e to the x is e to the x. The derivative of negative e to power minus x becomes plus e to power minus x. Let's close up the parentheses times e to the x plus e to power minus x minus the derivative of e to the x is e to the x, and the derivative of e to power minus x becomes negative e to power minus x. So let us close up the parenthesis and then copy down the last term, which is e to the x minus e to power minus x, and all is divided by e to the x plus e to power minus x to the second power. Now, as we talked before, we need to distribute the quantities into parentheses and then do a little bit of algebra. So if I just distribute e to the x into parentheses, what I get e to the x times e to the x, which is e to 2x. When I multiply e to the x by e to power minus x, I can write one base and add the exponents, which is 0. Then I'm going to distribute e to power minus x into parentheses. So we get plus e to power minus x times e to power x plus, then you have e to power negative x times e to power negative x, or e to power minus 2x. Then we move on to the next set. In the next set, we do the same thing. We take e to the x and then we distribute that into parentheses. What do we get? We need to be careful. Since we have a negative sign, let us put it in bracket. So here you have e to 2x minus e to the x times e to power minus x, then distribute e to power minus x with a negative sign in front of it into the parentheses. So this guy becomes minus e to power minus x times e to power x plus e to power minus x times e to power minus x, or e to power minus 2x. Divide everything by the denominator to the second power and leave it as it is. So here you have e to the x plus e to power minus x to the second power. Very good. So let's take a look at our numerator. Our numerator is e to 2x plus, when you add these together, so let me just write this guy down here. You have e to power x minus x or e to power 0 or 1. So you get a 1 here. You have another 1 as well. Plus, this is 1 as well. Plus e to power minus 2x minus. Now inside the bracket, you have the same thing, same process. You have e to 2x minus 1 minus 1. This is just 1. This is another 1, and they have both negative signs in front of them. And finally, we have plus e to power negative 2x. Let's close up the bracket and do the division by the denominator to the second power. So you get e to the x plus e to power minus x to the second power. Ooh, a lot of algebra, but we can make it. This in turns is equal to e to 2x plus 2 plus e to power minus 2x minus e to power 2x, and these 2 is negative, a negative sign in front of it, so you get another 2 minus e to power minus 2x divided by e to the x plus e to power minus x to the second power. But please pay attention here. E to 2x and negative e to 2x, they are opposite of each other, so it cancel out. E to power negative 2x and negative e to power negative 2x. They cancel out. They're opposite of each other. So you're left with 4 divided by e to the x plus e to power minus x to the second power, that can be written as 1 divided by e to the x plus e to power minus x to the second power over 4. But what is this guy? All right, we're going back to the basic definitions, right? This can be written as 1 divided by e to the x plus e to power minus x divided by 2 to the second power. It is equal to 1 divided by hyperbolic cosine of x to the second, or you can write this as 1 over hyperbolic cosine to the second, or 1 divided by hyperbolic cosine, as you remember, is hyperbolic secant of x to the second, or in simpler form, you get hyperbolic secant to the second power of x. Okay, what was that? Let's go back to top. What did we do? We had the derivative of hyperbolic tangent. The derivative of hyperbolic tangent happens to be hyperbolic secant to the second power. Keep forgetting to add c. Hyperbolic secant to the second power of x. And this is the algebra behind it. We did the calculus part, we took the derivative, and we did a lot of algebra to show that, hey, this guy can be written as hyperbolic secant to the second power. And let me move this up. So now that we have the derivative of hyperbolic tangent, so now that we know that dx of hyperbolic tangent of x is equal to hyperbolic secant squared of x. By fundamental theorem of calculus, if you take the integral of both sides, the integral of hyperbolic secant to the second with respect to x is equal to hyperbolic tangent of x plus constant of integration. So as long as you have the derivative, you can easily take the integral of both sides. This is fundamental theorem of calculus. As long as you have the antiderivative, you should be fine calculating the integral.